Today we're going to see the process that we go about entering the computer model of this vehicle into CAMG and doing a simulation to answer some of the questions regarding the design of the seat belts or the bumper of the car. So in here we have the problem as we have stated. We have the car here going on a barrier test, okay? And we would like to look at the design of the seat belt as well as the bumper. So we have the data on injuries. Seat belts must be tested at 3,000 pounds, and the chest can sustain a force of 1,500 pounds. The seat belt area is 30 inches square, and shoulder strap and belt combination double that. So that's what the problem is. You're giving the mass of the vehicle passengers about 200-pound passenger, and then this values for the seat belts and the stiffness and damping of the seat belt. Same thing as for the bumper in here. We had gone to build the bone graft model as we see on the screen here, where the where we can have the representation of the vehicle here, the person, the seat belts, the bumper in here, and the wall, the barrier here. So once we have built this bone graft model, the question is how do we go about entering this into the CAMG software and performing the simulation? What I think would be helpful is to keep a copy of the image of this page as we go to the CAMG and draw it there. One thing that I want to say ahead of time is that once we know the bone graft model on paper, once we have it on paper, it doesn't matter in which order we build it, as long as the arrows and the that control the power flow are correct. The computer will name the file by itself. I mean the bone grafts by the bonds by themselves by itself, and will also assign the causal marks. So I think it's important to see that we have the connections done correctly now, and then we're going to put it into the CAMG software. So let's just make this into a window, look smaller in here, and see we keep it handy, at least part of the bone graft model, until we build the rest. So we'll go down here. Um, yeah, that's the window that we need. We'll put it over here so that we can see. And then we go click here, and of course we went to say new file. The computer gives us this clean space, and like I said, here we could go and start any way we want to. So in here we put this number. You were just gonna put the source of flow that you see here, and then we have the model of on the left hand side of the see we gotta see what's on the here. See on the R element, which represent the bumper in here, and so we're gonna go and say do this, and then we're gonna put the C element in here, and then the R element. Yeah, and we go back to our little picture in here. We we have this connection on the right hand side that needs to take place. Um, this is a one junction on the right hand side over here, which we have, and then this is connected to an I element in here, which indicates the vehicle, and then we have the 0 here, and then we have a 1. You see, deliberately I am not paying attention to the bond numbers. I let the computer do that for me. The bond graph numbers and elements, they are just to help us reference to a particular element. And then you have it like this, and I'm almost done. I once I enter the C element in here and the R element, which is representing part of the seat belt in here, this area, then I will be done. So entering this and this on the right hand side, which is the R element right there, and this is what I have. Yeah, okay. So let's reflect a little bit on what we need to get out of this, how we go about finding out that variables that we want, and what kind of variables can we get directly from here. So the computer is going to have 4 state variables in this case, because we have 2 i's and 2 c's, and then that means on the initial conditions we need 2 positions and 2 momentums. So this is the way that we specify the input to the system, is by telling them that the initial conditions, the initial momentum of the mass as well as of the person. So that's one thing. The other thing to keep in mind is that we need 2 positions. Are those seat belts in the unstretched position? You know, they are already there. Are they in equilibrium? I think that's what we're going to assume. So the displacement is going to be 0, but the momentums would not be 0. The momentums, one of them is going to be the momentum which is of the vehicle, which is the mass times the velocity, and the other one would be the momentum of the person, which would be mass times the velocity. The initial conditions for the spring elements, I would set them to 0, because we are saying, okay, springs are in equilibrium position, nor compressed nor stretched. So we have the bond graph model here on the right hand side, and let's identify what are the, first of all, what's the force acting on the person. This is the person right there, this bond number 10, and if we display E10, would be the force acting on that person, right? That's also another question is, what is the position of the person with respect to the vehicle? Because we don't want him to hit the windshield, and the problem is giving you a distance that is the limit between the initial position of the person and the windshield. So if it exceeds that, we know that it hit the windshield, right? So what kind of variable can we get as an output for that position? The relative position between the car and the person is given by the relative position of the spring here of this one is how much the seatbelt has stretched. That's obvious. So the the displacement or the stretch of the C element is what would give us that output. So in this case, that displacement is going to be a state variable, which in this particular case, if we look at the C element number 12, this Q12 is going to be the output that we are looking for. So the way we do this is we go over here and we say, okay, interface to MATLAB, please. And then the computer program says, okay, gives us some instructions, and if you play the place bar, you get a connection, direct connection to MATLAB. And so this is the connection to MATLAB is right here. You can see the program produced 4 files. It produced a CAMG mod file, which is the model file. It produced a QU file, which is the equations file. It produced a symbolic file and produced a numeric file. For both of these, the symbolic and the numeric files deal with operating in the S domain. Right now we're doing time domain simulation, which are these 2 files. So this contains the parameters of the system, the system is made of, and this contains the equations of the system. In fact, if you look at the bond graph model that we just had, you just keep it next to the one that we had on paper when we just do it. So let's keep that in mind so that we can refer to it during the simulation. So I am going to get a copy of this, a picture of this. One neat thing is I like this snipping tool in here because it allows us to do this thing. See, right there I can copy this and put it in my notes as I am developing this here. Alright, so this is your model on paper and this is your model on the computer. See, just gonna put it here so that we identify the bond graph model with the system itself. So what I was saying is right here, E10 is the force on the person. That's one of our outputs. And Q12, which would be the displacement of the spring with respect to the displacement of the seat belt with respect to the vehicle. So once we are in MATLAB, we are going to operate with those 2 files. This one, the model file, and this, the equations file. Just in case you want to take a look at the equations file, the computer did this and obtained the 4 differential equations, dq12, dp10, dq4, and dp7. Are the derivatives? We have 4 of those, and the individual constitutive equations, as well as those equations for the 1 and 0 junctions that complete the set of equations and make these individual equations act together as a set of differential equations. So in here, I am going to enter the values. Do you see what I mean here? For the sake of example, I'm going to enter some values that don't have anything to do with the exact problem, so that just to illustrate and get some output, but you will have to put the actual numbers, okay? And in this case, these two are 0, yeah, and Q4IN, this is also 0. Those correspond to C12, this, and then this other one right here, 4. Those are the initial positions. The momentums, we're going to have P10 and of course P sub 7. Those are not going to be 0 because those two are the product of the velocity times the mass. In the case of P10 is the person and P7 is the vehicle. Do you see it? Right here, see, P10 is the person and this P sub 7 is the vehicle. So this is going to be, I would say, you have this I10, and then I would say multiply by the velocity. Okay, and this other one is going to be I sub 7 multiplied by the velocity, v, right there. And of course, before this, you're going to have to define what the velocity is. If it is in miles per hour, or keeping everything in miles per hour, of course, the units of mass will also be different, or if you do it in kilometers. And then, so master the velocity here would be, we say 40 miles an hour or 30 kilometers. You know, you could just do that. And then you have initialized the initial conditions. And now the C sub 4 right here, C sub 4 is the stiffness of the bumper, and C12 is the stiffness of the spring, and then R would be the damping here, and R5 and R13. Those are the damping elements in here, and you are giving those values too in the problem. So, but right now we are just entering some numbers that we don't know, just for the sake of example, not because it has a relation to the problem. The F sub 2 is 0 because that's the wall. In here, C sub 4 C sub 4 is C is 1 over K. So you need to enter 1 over the K, which is the value of the, for C sub 4 is the value over here on this of the bumper. And that value, I believe we have. See, we have these values, the K's and the B's. So those are the numbers you have to enter. And here we could enter some numbers just for the sake of example, now that this really applies, but only so that we get some simulation. Hopefully we don't create a crazy system in here. This would be like 100 in here, and the other I10 is the person. Let's do this 10, and this C. Let's hope that this don't. And then you say the simulation should go from time 0. I'll give it to 5 seconds. If this is too much, we will see later on. Now the computer goes ahead and solves this CamGQU, which is the other file that we have available to us, isn't it? See, right here, this EQU file. In here, we have to specify what the outputs are, because you see in this mod file, you say, oh, CamG EQU is being produced, and in here is sample MATLAB output. So you're gonna get two figures. One is the PQ1, which is this Q12, two displacements and two momentums you're gonna get as outputs. And then the computer gives you another setup for obtaining the efforts. The efforts need to be specified on the second file in the CamG EQU file. What is the name of the ones that we want? E sub 6 was one of them, right? Remember? E sub 6 is the force on the person. That's, we could leave it F1, that would be at 0 here. But if you run this now with those numbers, hopefully we haven't produced a very crazy system. But in here, I have made it in such a way that I run the wrong file. We need to save this, okay? And then we have to run it from here, from this file, are the ones that, okay, hold on for a second. Okay, let me see. We have this symbol that is a funny one. Okay. Once we corrected that, the computer begins working. And of course, in this case, it has some problem because we haven't defined yet the parameters in here. See, those are defined here, and we did this over here. Well, why don't we just do this? The value of this is, what is this, I10 and I7 is, I10 is 10, and so the conclusion is we really need to put the numbers here, multiply it by, and this would be 100 over here. Okay. And so we run it again. And then we should be able to get something, and we do. These are the first ones, first plots of the simulation. But this is, of course, this is showing you how to get the plots, but you need to put the numbers that correspond to the problem. But that's how we run the computer simulation, starting from scratch and creating the bone graft model and going through the CamG and the two files, CamG mod and CamG EQU.